So we just want to look back what we have done in the previous lecture. We just want to summarize and look back and what we have learned so far. First of all, when you are talking about photochemistry, it is the interaction of light with the molecule. So which light is important? It is mainly the UV light. UV light ranging from 200 to 400 nanometer, or in other words, we also call it as a 2000 angstrom to 4000 angstrom. So this is the range of UV light. When we shine UV light, molecule undergo what? So the next question is, how much amount of energy we are giving to a molecule when we shine 200 to 400 nanometer to a molecule. So if we talk in terms of energy associated with the molecule is the range ranging from we'll call it as a not only say 40 to around, say for example, in 40 to 143 kilocalorie per mole. So when we shine UV light, we are giving energy equivalent to around say for example, as I have mentioned just now, 60, not only 68, around say 450. So say 70 to 143 kilocalorie per mole. This much amount of energy you are giving to the molecule. Now when we shine light, that is mainly the UV light, ranging from 200 to 400, which is equivalent to around 70 to 143 kilocalorie per mole, what changes takes place in a molecule? So molecule undergo, when we shine this much light, molecule under electronic excitation. What changes take place is the molecule undergo electronic excitation. So what are these electronic excitation? These electronic excitation are sigma to sigma star, pi to pi star, n to pi star, and n to sigma star. So these are the electronic excitations which are possible when we shine UV light, which is equivalent to 70 to 143 kilocalorie per mole. Now, what these excitations are? So, what happens? Molecule from bonding orbitals, which are electron occupied in the ground state, goes to an excited anti-bonding orbitals which are vacant. So, say for example, in terms of, say for example, if you talk in terms of energy, so these are bonding orbitals. We have this is sigma, this is pi, and this is an non-bonding. So and these are bonding orbitals, bonding orbitals, and they are electron occupied. And when we shine UV light, this goes to an anti-bonding orbitals. So it goes to this is pi star, and then it goes to N star. So molecule from N to pi star takes place if the non-bonding electrons are present in that particular molecule. And if you have a pi electrons, then molecule from pi bonding orbital goes to pi star, or it may also go to and sigma, and of course this is sigma star. So this goes to sigma star. So these are the electronic excitation which are possible. So what type of molecules and sigma to sigma star excitation possible? Single bond compounds having sigma bond. Compounds having sigma bond, like alkane and these electronic sigma to sigma star takes place. And in what type of molecule pi to pi star excitation takes place? Is it like where those molecule which has pi bonding electrons, say for example alkene, alkyne, even carbonyl. So for example, carbon also has a pi bonding as well as, so what in what type of molecules n to pi star excitation takes, or n to sigma star, the both those at or electrons, those elements which have non-bonding, that's just like oxygen, nitrogen, and phosphorus, silicon. So these elements have non-bonding electrons, and then in those molecules this n to pi star or n to sigma star excitation takes place. And then the next question arises, which excitation require minimum amount of energy? If you see here, so for example, I'll just draw 1 second, because this is energy, this is sigma, this is pi, this is n. This is sigma, this is pi, and this is n. These are electron occupied. This is bonding orbitals. Bonding orbitals. And then we have a pi star, and you have a sigma star. This is no and you have a sigma star. So these are anti-bonding orbitals, right? So when we shine light, the molecules undergo right. So you have this is anti-bonding orbitals. Means they are in the ground state. These are electron occupied, and these are electron they are vacant in the ground. When we shine this much light, wavelength or light equivalent to this much energy, the electronic excitation is n to pi star. And the question here arises, which excitation requires minimum amount of energy? This n to pi star. N to pi star excitation require minimum amount of energy, because you can see the energy gap is the minimum in any of these excitation. Which excitation require maximum amount of energy? It is sigma to sigma star requires maximum amount of energy, means shorter wavelength. Because we know that E is equal to h nu, the energy relation with respect to E is equal to h nu and h c by lambda, and then it is the inversely proportional energy, inversely proportional to lambda. Shorter the wavelength, higher in energy. And then these are the few questions which may arise when we talk of photochemistry. So these are the basic questions we must know when we are talking about photochemistry. When we talk of photochemistry, is the interaction of light, is which light, is mainly the UV light, how much amount of energy we are giving to the molecule. We are giving out energy roughly equivalent to 70 to 140 kilocalorie per mole. And what happens when we give this much energy? Molecule undergo electronic excitation from bonding orbital to anti-bonding orbital. Then which excitation require minimal amount of energy? This excitation n to pi star require minimum energy for the excitation, because you can see the energy gap is very little. And which excitation require maximum energy? Sigma to sigma star require minimum energy. One more thing which I would like to mention over here is that when we give this much energy, so this much energy, if you look at the commonly bonding orbitals which are present in most of the organic compounds, we have a carbon hydrogen bond, we have a carbon oxygen bond, we can have carbon halogen, this is a halogen bond, and then carbon bond. So these are the main bonding which is possible in most of the organic compounds, in like alkane, alkene, alkyne, alcohols and ketones and so on and so forth. So and this the typical energy associated with these bonds, the amount of energy required to cleave this bonding comes in this range. Between 70 to 140 kilocalorie per mole. So what I would like to impress upon you here is, when this much UV light is more than sufficient to bring about any of these excitation which is possible in any type of bonding which are present in the organic molecule. So now the question is, what are the different different radiative or non-radiative process? And so, for example, so when we shine light, say molecule, say for example molecule A in the ground state, say for example S0 state, the ground state, on absorption of light, mainly the UV light, 200 to 400 nanometer, or in terms of angstrom unit, 2000 angstrom to 4000 angstrom unit. So molecule goes to an excited state, and now these excited states are high energy species. They are high energy species, high energy species, high energy, high energy species. So number one and number two, they are short-lived. Short-lived. The lifetime of these excited states are very less. When we talk in terms of so this is S0 and then goes to S1. So this is the on absorption of light, molecule from ground state goes to an excited state. This is a singlet excited state, and this the lifetime of this singlet excited state is around 10 to power minus around 10 to power minus 6 minutes. And then this can, since these excited states are high energy species and short lived, they do not stay a very long time in this. They undergo deactivation process. So there are different it can come back to ground state by two different ways. Like it can come to ground state by internal conversion. This is a non-radiative process. Non-radiative process. Non-radiative process means it loses heat and it comes back to ground state, or it may also come back to ground state by a radiative process. This is called fluorescence. FLU. Can come back to ground state by losing light as well. It's called fluorescence. And then it can also come back to another excited stage is called as the triplet. This is the singlet excited state. Singlet excited state is the triplet excited. This is also excited state but lower in energy, and then this can come to this by inter-system crossing. So come back to triplet stage. For example, triplet stage is T1, and then the molecule from a triplet excited state can once again come back to ground state by radiative and both non-radiative process. It coming to non-radiative process, the inter-system crossing, or it can come back to by losing radiative process like phosphorescence. Phosphorescence. So just to summarize once again, the molecule in the ground state goes to an excited state. This is S0, S1, and then T1. This is called H nu. This is absorption. Absorption of light can come back to ground state by fluorescence, can come back to ground state by internal conversion. It can come back to triplet state by inter-system crossing. It can come back to triplet to inter-system crossing, or by a radiative process. The radiative process called phosphorescence. So there are So these excited states are high energy species on absorption of light, can come back to ground state by two different processes, radiative and non-radiative. So that's why it is the question asked what are different radiative and non-radiative processes. So the excited state coming back to ground state means it is just an energy wasting process. Whatever energy you have given, molecule absorbs light, goes to an excited state. These excited states are high energy species and short-lived, can come back to ground state by radiative process. Just a solid line is radiative called fluorescent. Non-radiative process is a wavy line, internal conversion. Or it is from singlet to triplet, it can come by intersystem crossing. Non-radiative process from triplet to ground state can come by both process, radiative as well as non-radiative process. Radiative is phosphorescent, non-radiative intersystem crossing. Lifetime of a singlet excitation is shorter, around 10 to power minus 6 minutes, and then triplet excitation is slightly higher, is around 10 to power minus 3, 10 to power minus right? 10 to the minus 3 seconds, right? So these are these are the few radiative and non-radiative processes, and the lifetime of these excited states are. So and now the next question arises: what is the position of singlet and triplet excited states in terms of energy? So, for example, this is energy molecule from S0 can go to S1 state. S1 state also can go to S2 state, also can go to S3 state. So this is on absorption of light, H nu. The molecule can go to S1. It can also go to S2, and this can also go on absorption of light to S3. So molecule from ground state can go to either S1 state or S2 state. So, and then molecule from S3 it can come back to ground state through internal conversion. From it can go, and then from the lower ground excited state it can come to triplet state. So this is the T1 state. This is the T1 state. This is the T2 state, and this is the T3 state. So this is the position of the different, and then from triplet it can of course come by radiative and non-radiative process. So these are the, as the question asks, what is the position of singlet and triplet excited state? These are the S1, S2, S3 molecule from ground state on absorption of light goes directly to either S1 state or S2 state or S3 state, and then from these excited singlet state it can come to ground state first, and then it can deactivate to T1, and then it can come to T2, and of course S2 can come to T3. These are the positions of this. Now, as I have mentioned, the molecule from molecule A on absorption of light can go to excited state, and these excited states are high energy species and short-lived. How? What are different ways for this excitation? So there are two different ways we can bring the molecule status by direct excitation. Say for example, A directly absorbs light, goes to an excited state. Now for this the lambda maximum, it is important to know the lambda maximum for this molecule, so that we are giving the proper light for the excitation of this molecule, which absorbs light and goes to excited state. So this is the direct excitation. Molecule A on absorption of light goes to excited state. There are some indirect excitation where a second molecule is used. We call it as a sensitizer. So for example, S is a sensitizer, and then it absorbs light and goes to mainly UV light, goes to an excited singlet state, and then it can go to excited excited triplet state, and then this can transfer energy. It can transfer energy to the molecule A, transfer energy, and molecule A goes to excited triplet state, and then S come back to ground state. So this is here the what we have done is we have directly excited the molecule. That is called direct. Direct excitation is called indirect. Indirect excitation, or in other words, we call it as sensitized excitation. Sensitized excitation, whereas the molecule is going to excited stage, not directly absorbing the light, but it is absorbing by a second molecule, we call it a sensitizer. Sensitizer absorbs light, goes to an excited singlet state, and then it can go to excited triplet state via inter-system crossing, and then it can transfer energy. Energy to molecule A, whose photochemistry we would like to study. The molecule A goes to an excited triplet state, and then the sensitizer comes back to ground state. So this way of excitation is called as the indirect excitation. So now we have already answered the position of S1, S2, S3. We have also looked at the positions of T1, T2, T3. We have also we have also looked how this excitation can be takes place either by a direct excitation where molecule directly absorbs light, goes to an excited state, and this is for this we must know the lambda maximum so that we give proper light for maximum absorption so that the molecule goes to an excited state. And the molecule can brought to the excited state by indirect excitation. For this, a second molecule is used, such as S, is called as sensitizer, and this sensitizer absorbs light, goes to an excited singlet state, which can come back to excited triplet state through intersystem crossing, and then this sensitizer through electron transfer energy can to the molecule A, whose photochemistry is to be determined, goes to an excited triplet state, and the sensitizer comes back to ground state. So these are the two different ways through this. One more thing which we would like to now let's see what is now the changes in excited state. So what changes in excited state takes place? So first is the molecule A goes to an excited state. This is the ground state. This is the excited state. So these excited states are high energy species. They are short-lived. So as we have seen here, they are high energy species, say S0 to S1 to T1. So you can see it is a high energy species. So it is not, these high excited states are not only they also undergo structural changes. We have also discussed this in the previous lecture. Say for example, when molecule on absorption goes to excited state, these are not only they are high energy or short-lived, but they also undergo structural changes. Say for example, we have an alkene in the ground state, and then on absorption of light goes to an excited state. Now these excited states are no longer double bond. The double bond character in the ground state, the excited state double bond character is lost. They are now they no longer, they are dialectically species, and not only changes. So is a structure which is this is a planar. Now in the excited state they are pyramidal. pyramidal structure. So the molecule also undergoes structural change in excited state. They are high energy species, short lived. They are also undergo structural changes, such as alkene in the ground state is planar. When it goes to an excited singlet or triplet state, it can also undergo double bond character is lost. They are dialectical species, and there is a bond length which is 1 I mean the around the bond length which is shorter in double bond. Now it goes to approaching a single bond character. There is a bond length also increases, and it is approaching more towards ethane bonding 1.20 to 1.34 angstrom unit. So the structure which is planar excited state, they are changing the pyramidal structure, same as the carbonyl, which is planar in the ground state, and when it goes to an excited state, now the double bond character is lost, and then the planar structure is now pyramidal structure. So the structural changes also takes place in the ground. So this is what is more emphasis in this. Now the as I have mentioned here, these the indirect excitation can be brought about by energy transfer. So, for example, in this indirect excitation, say for example, for indirect excitation, we need a sensitizer in the ground state. On absorption of light, goes to an excited singlet state, and then it goes to excited triplet state, and then it transfers energy. So energy to molecule A, and the molecule A goes to an excited triplet state, and then this. So it is also possible that there are some sensitizers which transfer, instead of transferring electron, there are some sensitizer which transfers electron. So sensitizer, in that way we have a two system, a donor plus acceptor in the presence of light. Donor is an electron rich species, acceptor is an electron deficient species. This is a donor, electron rich, and the acceptor is electron deficient. And then in the presence of light, there is an electron transfer from donor to acceptor. Donor goes to an radical cation, plus acceptor goes to a radical anion. So this is a electron transfer reaction, is an electron transfer reaction, and this is induced by light. So it is called photoinduced electron transfer reaction. Again, it is two types: homogeneous and heterogeneous. So the homogeneous electron transfer reaction, where the donor and acceptor both are soluble in the medium. Say for example, a lot of photoinduced electron transfer reactions have been studied by reacting with, say for example, amine with alkene, or alkene with dicyanoanthracene, and so on and so forth. So both donor acceptors are soluble in the medium, whatever solvent we take, like acetonitrile or benzene or methanol. So it is a homogeneous mixture, it is a single phase reaction. In heterogeneous mixture, we have already talked that it is a one phase, two phase reaction. One component is soluble, other component is insoluble, and that is and hence it is a biphasic reaction, or we call it an example is a semiconductor mediated reactor. If we have a semiconductor like titanium dioxide, and when we do the reaction, titanium dioxide with an alkene, and then in the HNU. So in say for example, in the reaction is methanol, or in water, methanol or protic solvent. So in methanol, this titanium dioxide is a semiconductor material. It is neither soluble in water nor methanol. So it's a biphasic reaction, and the reaction takes place on the surface of this. So and hence there is a electron transfer reaction from here to, first it goes from valence band to the conduction band, and then electron and hole pair, which once again takes place, redox reaction takes place on the surface of the catalyst. So this is so photoinduced electron transfer. So indirect excitation can be brought about by two ways. Number one, by energy transfer reaction, and where the second one is electron transfer reaction. Is this one where donor acceptor use, where the donor gives an electron, accept an electron, we generate a radical cation. A radical anion species is called photoinduced electron transfer reaction. The electron transfer reaction initiated by light, and it is again two types: homogeneous photoinduced electron transfer reaction and heterogeneous photoinduced electron transfer reaction. Homogeneous electron transfer reaction is a single phase reaction, both donor acceptor are soluble in the medium. Heterogeneous photoinduced electron transfer reaction is a biphasic reaction in which one component is soluble, other component is insoluble, and reaction takes place on the surface of the medium, and hence it is possible to recycle or use the catalyst again and again, and it has a lot of application from recurring point of view.